right. Thank you, everybody, for coming out. My name is Laiacano. I work at Tumblr. I used to do digital signal processing stuff. I was an electrical engineer for a long time. And then I stopped, and now I work with big data because it's cooler now. And so, are we good? Yeah. So I came to this realization that it's pretty easy to combine these two things, relatively speaking. And so I wanted to start doing this. Paul asked me to give a talk, so I'm really excited to be talking about this. And so what I'm going to talk about mostly is signals and filters. I assume, has anybody done digital signal processing stuff before? Okay, who knows what a Hamming window is? Okay, so well, all right. I was just trying to get a gauge. So I'm assuming that people don't know anything about signal processing, which is awesome. It seems like most of you will get something out of this. So I'm going to talk about sampling, which is how you go from representing a signal in the analog world to the digital world. You either record it or you calculate it or something. What that means in the frequency domain. There are two main classes of digital filters, or filters in general. They're called finite impulse response and infinite impulse response. And I'll say FIR and IIR. And then we'll get into Scalding. Scalding is what we're going to be using to actually implement this type of stuff at scale in Hadoop. This is not a talk about Scalding, but I'll just give you enough syntax that we can move along. And then we're going to apply it. We're going to filter 140 million signals, and then we're going to see what that looks like with Tumblr blogs. So for anybody that doesn't know anything about Tumblr, we're a blogging platform. There's 140 plus million blogs that we host. It's free to sign up. It's fun to use. The big signals that we've got a social graph that works similar to like Twitter or Instagram, things like that, as opposed to Facebook or LinkedIn, where it's a directional graph. I can follow your blog. I can like things, I can reblog stuff from it, so it'll appear in mine. You don't have to follow me back in order for that to work. So we'll be working with that social graph a little bit later. And so this is a signal. It's, say, daily users on a website. You've got two main components. You've got a sort of trend, like a seasonal effect maybe. Maybe your website's more popular during football season or something. And then, so that's the big thing. The smaller one is a weekly variation. So that signal you see in there is 7 days from peak to peak. Anybody that works for a website has probably seen something like that before. Like when people use Tumblr on Saturdays and Sundays, they're during the week. If you work for some business software, they probably use it more during the week. And so the key component here to think about is that this is a signal, a digital signal. And the main things are that they're evenly spaced measurements, time-wise, right? It's 1 day exactly between each of these, and that's crucial to have that consistent spacing, and there's no missing data. We don't have any, like if we were missing a day, we'd have to infer it somehow or put a 0 in there or something. So you need a complete time series. The other thing is that there are two signals here, right? There's the one that has a large amplitude and a low frequency, that's the trend. And the other one has a smaller amplitude with a higher frequency, and that's the weekly variation. And so we can think of these signals as being sums of pure sine waves with different amplitudes or phases. I'm not going to talk about phase, but that's an important thing in the real world. And so we can generate this signal or by combining all of these pure sine waves, or we can take this signal and break it up into all of its different pure sine waves, see the amplitude of each. And so that pulling these things apart is a crucial element. So if you have this website and you know you have this weekly variation, it's not interesting. So you run a 7-day moving average, right? It's the thing that everybody does. It takes, today is Wednesday, so take from last Thursday until today, count the number of active users, average them, and that's the output for today. This is something that every business analyst has probably done at some point. This is the simplest digital filter. And so we'll talk more about how to generalize this and apply them. And so these are some of the words that I'm going to be saying a lot. Signal, I've already said a ton of times, right? And it's just a time series of data. When I was doing engineering stuff, this was either volts or current or something like that. Now I deal with things like posts and impressions and follows. It's different, but it can be treated the same. The sampling period is the time between all of these samples. So before it was 1 day. If you're working with audio frequency, it's the sampling period. Well, the sampling frequency, which is the inverse of CDs, is 44 kilohertz, right? 44,000 samples per second. And the reason that they chose that is there's this thing called the Nyquist frequency, and that is the highest frequency that you're able to represent digitally. So the human ear can pick up roughly 20 hertz to 20 kilohertz. So if on a CD you want to represent that highest frequency that you could hear, it means that the CD has to be sampling these actual audio, the waves coming out of my mouth, has to be sampling those somewhere higher than 40 kilohertz. Otherwise, bad things happen. And so I'll show that a little bit later as well. And so that's all sort of sampling and time series or time domain stuff. On the frequency side, we've got filters, right? Filter, this is like a Wikipedia definition that I hacked to make it less clear, I think, but I think we all know what a filter is, right? Like you want to, get rid of noise in something, or you want to remove your weekly trend, things like that, right? You'll have a bunch of frequencies going in, and you want to make sure some get through, maybe amplify them, and you want to make sure that some don't. There are other types of filters as well, but these are the ones that we're working on. The stop band and the pass band are the sections of frequencies that you want to either block from getting through or allow to get through. And the cutoff frequency is the sort of dividing point there. And so to think about signals, I think this is a pretty cool picture of smoke signals because they are kind of a digital signal, right? It's not this continuous thing that's growing up. People are deciding when to emit a smoke thing or whatever. So it goes back really far. I tried to find something about smoke signal communications and how it might be related to digital communications, but couldn't find anything, unfortunately. So this is what sampling looks like, right? We've got an analog signal on the left, and it's a sine wave, right? We've all seen sine waves before, and when we're working with it digitally, we need to actually look at it and make a measurement, right? And so I'm making 10 measurements for every period of this sine wave, and I don't know what the original thing actually looked like. All I know is that this red line that I've drawn is what I have to work with. So it looks pretty good. You might be able to see on the top, it's rounds a little bit higher where the red one is flat, but we can pretty clearly see that this is the thing that we're working with. However, if I sampled at one sample every period, you have no idea, right? It's the same height every single time you sample. So when you're working with this on a computer and programming, which we all do, you're getting a flat line, right? There's no variation in your users or whatever. It's completely useless. And if you do 2 samples, which I said is you have to have at least 2 samples in order to represent this frequency, you can see the thing's going up and down at the right rate, but it looks like a zigzag where it's really not a zigzag. There's a lot of missing fidelity. So when working with digital signals, you really have to be aware of what frequencies are there, and you have to do some sanity checking on, are the numbers in my program or what I'm actually physically working with. It's less of a concern when I'm working at website scale, because things don't change faster than we can write them down, really. But if you're going from some sort of analog signal into digital, this is very, very important. And so the next big part is filters. I really like this analogy of a coffee filter, because if you think about what a coffee filter does, right? It takes 2 inputs, dry ground coffee beans and hot, clear water. And it blocks some of it and it lets some of it through, and what comes out is hot black coffee at the end, right? And if you think of a filter where you want to let one thing through and block another, if this was a perfect filter in that sense, you would put these things in and you would get hot water on the bottom and ground coffee beans dry in the filter. So real signal filters work in the same sort of way where you're able to block most of it, right? Most of the grinds are still in your coffee filter, but enough went through to turn this into a delicious beverage. And likewise, you know, most of the water made it through, but the grinds are still going to be wet. So if these are your two sort of frequency bands, your stop band and your pass band, you're going to be able to block most of it, but not quite all of it. And so if we've got a sort of filter like this, right, and signals are often viewed as just passing through a filter continuously. You can do this in real time. You can do this, we're going to do it in batch mode. But the idea is, when all of these block diagrams are drawn, you have some signal, it goes into a black box that is a filter, and then you have some other signal coming out. And so we're going to go through, we're going to take this input, and we're going to turn it into that output by filtering it. And so the first thing we need to do is we need to decide where's our pass band, where's our stop band, right? So this is in, the x-axis here is frequency, right? Hertz or something. And so the Nyquist frequency at the end is the highest represented sample. That's why it's at the end. So that, in this case, is going to be 500 hertz because that's just the sampling period I chose. And so we want to let that low frequency trend go through, and we want to stop everything else. But like I was saying earlier, it's not going to be perfect. It's going to be more like this, where you're not going to be able to fully reject everything below the cutoff and fully, or above the cutoff rather, and fully accept everything in the pass band. So we're going to have to kind of deal with that, but it won't be bad. And so we talked about filters, but I haven't talked about how to actually, what it is actually made out of, how you actually apply it, things like that. We saw the moving average earlier in the beginning, and this is what you're doing, right? You're taking some input, X, you're multiplying the current value and the previous 6, so total 7 values, multiply each of them by 1/7, add them all up, that's your weekly average. And then you increment t tomorrow, and you do the same thing again. It's pretty simple. You can, there's a function in R called filter that will do this for you. A FIR digital filter is that, but instead of having 1/7 for all of your values, you have to choose this list of coefficients. So you have up to n coefficients. You do the same thing. You multiply today's value by the first one and so on, add them all up, that's your filter output. And choosing these coefficients will make it either, they decide what the cutoff frequency is, they decide if you're going to let high or low frequencies pass through and block the other. All of that comes down to deciding these few coefficients. So all the machinery is exactly the same for most types of, all of these class of filters. We just need to figure out what to actually put in there. And there's the R function, filter. You give it an input value, vector X, and you give it a filter vector H, and it gives you the output, which is nice. So before we actually apply it, we need to think about what this looks like in the frequency domain. So this noisy signal is something that I made in R. It's not really noise per se, it's just a sum of 3 different frequencies. The lowest one is 1/2 hertz, that's the frequency in green. Has an amplitude of 1, you can clearly see that, and then the other stuff that you can't clearly see unless you zoom in, there's a 250 hertz signal and a 400, and those have smaller amplitudes. So, am I cutting out? Is everything all right? So if you split this apart, it uses the Fourier transform. I'm not going to speak too much about this Fourier transform, but it's basically just an operation that will take this input, split it into as many frequencies as we can possibly represent. In continuous time, it would be an infinite number of frequencies, but we're working in discrete time, digital, things like that. So it's somewhere between 0 and 500. You can see there's a huge spike near 0, that's the 1/2. There's a slightly smaller spike at 250 and an even smaller one at 400. So this is what we've got going in. We know that. And so we want to filter out the 2 higher frequencies. We want to get rid of the 250, we want to get rid of the 400. So to do it, you go to a website, because other people have built all of these tools and they're free and they're online. You can do, MATLAB has an amazing signal processing package, but you don't really need it for simple stuff like this. So I went to this website, and the numbers are tiny on my screen. So in this box here, I said between 0 and 250 hertz, I want the signal to pass through, or 200 hertz rather, I want the signal to pass through. And from 250 to the full 500, I want it to block as much as possible. And this is called a Bode plot, and this is on a log scale. The ripples and things like that are sort of unavoidable, like those arches. But they're very far down. 40 dB is pretty significant squashing for a signal like this. But you really just got to go in and say, this is what I want, this is what I don't want, and it gives you that box over there on the right, and those numbers are the filter coefficients. That's H. And so you can fiddle around with like the pieces you want to keep, the pieces you want to get rid of, and it'll just keep updating those numbers for you. When you're done, you grab them and put them in your program, and you're good to go. So I did that, and this value of 8, it gave me 21 numbers. That's them on the bottom, and I used the filter function in R to send that noisy signal through, and this is what I got out. It looks nice and clean. You can see the 400 is completely squashed. I don't know if you can see, there's a tiny little blip at 250 hertz. That's what ended up making through. That's why I made sure that I put the cutoff right at where we have some signal, so you can see that. And so that's the idea, right? You're constantly just doing essentially a weighted sum of the most recent values you've seen coming in from your signal. And it seems to me like it's a pretty simple thing, but it's extremely powerful. The other class of filters that I mentioned are called infinite impulse response. And so this is the difference between the two. The one on the left is what we've seen before, finite impulse response. The one on the right is that plus another piece. And that other piece is a new set of coefficients, which I call G. And instead of multiplying previous inputs, we're multiplying previous outputs of the filter. And so I'll explain why this is called infinite, but they're a lot more powerful. And also anything with the word infinite in it, you should be wary of. Infinity is a really bad place to be. So they can be more powerful in the sense that like the transition between your stop band and pass band can be much sharper, but it could hurt you in a way. So I keep saying impulse response, and this is what an impulse response is before I show why one is called finite and one is called infinite. This is a delta function. Who here has heard of a delta function, impulse function, things like that? Good. It has the value 0 everywhere, except at time 0 it has the value 1. In continuous time it would have the value infinity, but fortunately we don't have to deal with continuous time. So what we're going to do is we're going to take this signal and we're going to send it through our filter. And it sounds kind of boring because it's just one point, but what you do is you get a good picture of what this filter is made out of, right? Like what it looks like. You get a good snapshot of it. So I did that for 2 filters. The one on the left is our 7-day moving average. It's a simple example to work through. On day 0, it has a value of 1, so the average is 1/7. On day 1, the input is 0, but the previous day was 1, so it has a value of 1/7, and so on. So it just traces out for 7 days, that's the value. And then after that, it's gone. Everything that this impulse could give to the system has been used and thrown away in a finite amount of time. The one on the right is infinite impulse response. So the idea is that on day 1, you take your input, take half of it in this case, and that's the output. On day 2, you take the previous output, 1/2, take half of that, so 1/4 is your new output, and so on, right? And so that initial 1-point impulse actually, it approaches zero asymptotically, but it's always there, right? According to a mathematician. I'm an engineer, I would say that at point 10 it's completely gone, but that's fine. But the thing you have to be careful about is what happens if I set that value instead of 1/2 to 1.1? Well, this is called positive feedback. Every day you're going to take the previous output, make it bigger. Take the previous output, make it bigger. This is really bad. I don't think any filter design tool you ever use will give this to you as a result. But if for some reason you messed up, this would, I mean, I've destroyed electrical components and things like that by trying to jack voltages up higher than they really should. The last picture of an input response is, this is the one that I designed in this tool. It's got this nice, pretty symmetric shape to it. Does anybody recognize that shape? It's a sinc function. The sinc function is the Fourier transform of a box function, which was something that takes the value of 0 everywhere except from, say, -1 to 1 and is the value 1, or any width, right, symmetric around 0. Taking the Fourier transform of that will give you this. So it's just sort of an aside, but most filters that you design will be symmetric like this and things like that. Moving averages are kind of like a hack, but you know, they're a very, very special case, but they're ones that I think everybody understands. That's why I'm using them. And so, quick recap on FIR filters specifically before we move on to other stuff. You're really just weighing, you know, we're taking a weight of sum of your previous n inputs, like a moving average. In order to actually use this and apply it, you need two things. You need, if you're doing it in real time, you would need the previous n inputs, x, and you would also need this filter coefficient array. If you're doing it in batch, you would obviously have the whole vector input x, which is what we're going to do next. So at Tumblr, we're starting to use Scalding a lot more. It's developed by Twitter. It's excellent. This is their new logo, I guess. So it's a domain-specific language. It's written in Scala, and it's sort of a wraparound cascading. And cascading is yet another sort of workflow language that makes it easier to write MapReduce jobs. Usually on Hadoop, you can run them locally if you've just got a whole bunch of data on your disk that won't fit in RAM. But it's really nice to work with. Scalding is similar to Pig. If you've used Pig, a lot of people say it's similar to Hive, but on the skin it's really not at all like Hive. Hive is like MySQL, but in Hadoop. Pig is more like if you had to explain MySQL step by step, that's what you would type. It feels like real programming. I don't know, does everybody here use R and Python? Pretty much, yeah. So it's been a while since I've worked with like compilers and a type system and things like that. It felt great. I don't know. It feels good to get back into it. And so we're building a lot of libraries internally in this. We've got stuff to load all of our data sets and make sure that you know, everything's formatted correctly and whatnot, and any corrupt data is thrown away. We've built naive Bayes classifiers and statistical tests and things like that that are really fun to run at scale, meaning terabytes of data. So slightly less general overview of Scalding. If anybody's used Plier or Pandas, it's got this split apply combine paradigm where you take a data frame or a table or whatever, in this case they call it a pipe, split it up into groups, apply something to each group, and then put them all back together. So each of these pipes, which is essentially a data frame, has one or more columns. We call them fields. And you can easily apply row-wise computation. So adding two things in the same row, maybe you make a new field as a result. Use map for that. If you want to do a field-wise operation, meaning like, say you want to get the average number of posts per blog or something like that, or the total number of posts per blog. You group by the blog ID, and then you perform a function on that group, which is the I don't know, count function. So here's a quick little hello world, this is what the actual syntax looks like. There's not a ton of overhead if you've used Java a lot. There's a lot of overhead if you've used Python a lot, but it's really not that bad. So we've got a method, or a class actually, called load posts. It will go and grab all of our Tumblr post activity data, who posted it, where they're from, a little bit about the content, what type of post it is. We've got a type to post system. It could be a photo or audio or a link or text or whatever. So we get some information about that. And what we're doing here is we're going to group by the blog ID, and we're just going to count the size of that group. That'll give us how many posts there were for each blog. And then from there, we're going to call that post count. From there, we take that post count, send it to this other little anonymous function that takes this PC int thing. That'll return a Boolean saying whether or not they've posted less than 50 times. And then filtering out, and this is not the filtering in the sense we were just talking, this is just like, do I keep this row or not? So it looks like what we're doing here is a sort of verbose way of saying, give me all of the blogs that have posted at least 50 times, keep only the fields called blog ID and post count, and then write it to a tab separated file somewhere, right? It's, you know, this is basically in Hive or SQL, this would be like select blog ID, count star, group by blog ID. I guess in pandas or implier, it looks sort of similar to this, but this is the idea, and you can do, there's so much going on here behind the scenes, there's a lot that you can do. I'm not going to get into it a whole lot here. There's some really good resources. Their wiki is pretty well documented for what they cover in the wiki. Edwin Chen, who used to work at Twitter, I think he's at Google now maybe, he made this blog post about building recommendation systems off of what people tweet, right? So they look at Foursquare check-ins by people tweeting like I'm here, or they do TV show recommendations by people tweeting I'm watching this show right now. And it's all built in Scalding. It's pretty clear, and it's got some convincing results. Reading that blog post really helped me like kind of realize the power of this stuff. And then the source code there's so many undocumented features in the source code. You kind of have to dig in a little bit, but there's a lot of gold nuggets in there for sure. So we're going to use this to start filtering signals. And we're going to do it by thinking about matrices instead of streams of data or things like that. And so if we take, this is our input data, right? This noisy green line, time is going down, I guess. And so when we're doing these FIR filters, what we're doing is we're taking it, we're aligning it at the very top, and multiplying the coefficients by the data values, summing them up, that's the output. Then we go to the next place. We do the same thing over and over. And what we're doing really is a dot product of these coefficients and the input values. And I put a little X over the hat just to say that every time we do this, the output Y is using the same filter, but it's using a different slice of the input, right? The X hat is totally made up symbol. So we can think of this another way, which is instead of taking a different piece of the data, we can make this filter just expand it out by adding a bunch of zeros and doing a dot product of the whole thing. The result will be the same because all those zeros will just make, the multiplication will be 0, they won't add to the sum. So we're doing the same thing, but in this case, instead of sliding the filter through the data, we're kind of, or rather, I guess, sliding the data and keeping the same filter, we're modifying the filter, keeping the same data. So I move the hat. But what this now is doing, really, is we're taking a input vector, multiplying it by a whole bunch of other vectors, and then aligning the results. That's just, in this case, row vector multiplying this matrix of filters, right? So the red part is the filter that's moving through. As you do these matrix multiplications, you're really just applying it over and over and over, sticking the output value, in its correct place. Is this working for everybody so far? You're all with me? It's a quiet crowd. So this is for one operation, right? What we've just done is added a whole lot of overhead. We're multiplying tons and tons of zeros. It's kind of annoying. Why do we have matrices? We could just use a filter function. But now we can add as many of these inputs as we want, turn that from instead of a vector into an input matrix, multiply that by the filter matrix, and what we'll get out is another matrix the same size as the input of all of these filtered signals. So in this case, I've got n blogs. Like I've got 140 million blogs. No reason I couldn't do it that way. But it's going to be pretty big. And so this is some R code to basically do that locally, right? It's very small. I take, I make a matrix of 4 signals. You can see x, 1, 2, 3, and 4. This is how you construct a square wave. It's the sine of 1 hertz plus 1/3, the sine of 3 hertz plus 1/5, 5 hertz, all the way to infinity. I just have a little piece of it here. So x4 here, I'm saying, is going to be a square wave. We'll take that data frame, turn it into the matrix, and then we build a filter. I use this function called toplets. A toplets matrix is something like this, where each row is like a shifted version of the one next to it. This is, I realize now, this is a sort of special case. The R toplets function, don't use it because you can read about it on Wikipedia, but they repeat not only on the rows, but also on the columns. On my GitHub, with stuff about this talk, I have a function in Julia that will build the right matrix. Either way, you build your filter, and then just do this matrix multiplication at the end, and you've done it. You've applied your filter 4 times. And so this is what those inputs look like, right? The first one is just a sine wave. The next one has a higher frequency and a smaller amplitude. The next one is even higher and even smaller amplitude. And then the sum looks kind of square, right? It's fairly flat on top. It's fairly steep in the middle or in the transitions. We apply that filter, and you get this as an output. It's a low-pass filter that we're applying in this case. So the lowest frequencies stayed pretty well. The next one down was attenuated sum. The higher frequency still is attenuated even more. And the interesting thing to look at is the result at the bottom. We've turned our square-ish signal into a mound-ish signal. And when you're working with digital signals, a lot of times square wave is used as like a clock, right? Like you need to perform an action every time this thing rises. There are a lot of triggers that you can set in digital hardware. And so the time that this thing takes to rise is very important because it's not a 0, it's not a 1, it's like somewhere in between. And you want that to transition very quickly in order to get good timing on your, I don't know, sampling or taking a picture, whatever it is that it's doing every time that thing rises in like actual hardware. So what we did by filtering this is those black lines are the same width apart. It's low, I hope everyone can see it. We've expanded how long it takes to actually rise. It has the same kind of overall frequency, but that's the main change that we made to it here. And I thought this was a pretty good way of actually visualizing like how the different components were affected and things like that. And so we're going to do this in Scalding, which has a matrix library, which is super convenient for us. It stores data, a sparse representation of the data. So it doesn't store like an enormous square. If you have a square matrix, it stores a pipe, like we were seeing earlier, with 3 fields in it: the row ID, the column ID, and then the value that exists there. Awesome for sparse matrices because you don't have to represent a ton of zeros. It assumes that if something's missing, it's got the value 0. And that's what we're going to be working with. Like as you saw in that thing, it was mostly zeros. Some of the stuff they have built in, they have a bunch of norm operations you can do. You can invert a matrix, which is awesome. Add, multiply, subtract, things like that. Someone, I think it's people at Etsy are working on QR factorization if you like really want to go crazy on inverting matrices and stuff. They're also doing, there's a lot of work going into doing SVDs, or at least partial SVDs. And that link will bring you to more information about it, I guess. But it's, I've only played with it a little bit, enough to kind of do this and a few other things, but the matrix library is pretty great. It's not as good as just working in MATLAB or something like that, but you know, the idea is to scale. And we're going to use this on our social graph, right? There's over 140 million nodes, 3.5 billion edges. Where an edge is, you know, if I follow you, that's a directed edge from me to you that appeared at a certain timestamp. So those are the 3 columns we have. We're going to calculate first the number of followers per day for every single blog, apply a moving average to all of it. And so here is the code to do that. So most of the code is really just generating this follows matrix, right? We're going to take the input data. In this case, we're only filtering out the last, we only want 1 year because, I don't know, you need a limit, I guess. We're turning those actual timestamps into dates so that we can do this per day, then grouping by the blog ID that's receiving the follow, receiving the edge, and day. And so that size will give us follows per day for every single blog. There's going to be a lot of zeros. I've got like 8 blogs and none of them got any followers today, so that's 8 zeros in this thing. So, and then there's just a toMatrix function. You tell it that the ID is a date, or the date is a string, the ID is an integer, and then the number of follows is a double. And then we've got this tuplets function again. This is one I had to write that builds a pipe with the filter as it's aligned perfectly. The input is the actual filter you want, and then the number of rows and columns that it's going to need, and it'll build it for you. And then you just take your follows, multiply it by the filter, take the transpose of that, and you've got your results. So, I mean, that line 14 right there is doing all of the filtering for us, all of the stuff on, you know, hundreds of gigabytes in this case, but it could very well be more. It's pretty awesome to think about. So once we do that, we've got a bunch of smooth signals, supposedly. I'll show them to you in a second. But we want to actually do something with it, right? Just filtering some stuff doesn't, I don't know, it's just still a bunch of data in our Hadoop cluster. It's not getting us anywhere. So we want to find blogs who have accelerating follower counts, right? So if today I have 100 followers and I gain 1, that's the derivative of that. So the velocity is 1. And if tomorrow I get 2, then that means it's positive acceleration. If the next day I get 3, then it's more positive acceleration. If the day after that I get 2, it's come down, right? So that's the end. What I want is to find a blog who is just exploding, like getting more followers than the previous day for the longest time. And so I grabbed a couple of blogs and I did this. And so these are just sort of 3 examples. I couldn't put the names of the blogs because we don't publicize follower counts the way Twitter and a lot of other people do. There were some pretty good reasons for it around like follower churn and, I don't know, perceived reputation. We just want people to like do good stuff, whether they have 5 or 5,000 followers. So anyway, the first one is actually an advertiser. Those big spikes are when they run ads. They get huge, you know, thousands of followers a day. Blog B is this sort of meme blog that blew up, was really popular for a little while, and then died down, but apparently didn't die down as much as I thought it did. And blog C is, it's one of the more popular kind of trends on Tumblr. It's like, I'm trying to think of, does anybody follow the DevOps reactions blog? Have you heard of this? So it's that, right? It's like, you know, a house burning down, and it's like, when I'm on call, and like, everything's awful. So the blog that really started this sort of meme that got copied everywhere was super popular. It was on the Today Show, I think, or something. So that's them, right? And so what I did was I looked at, these are the number of new followers per day. So the actual Y value is the velocity, and what I want to see is if the value today is higher than the value yesterday. If it is, then it's going to be blue. If the value today is less, then the number of new followers today is fewer than yesterday. You're still gaining followers. Then it's red. So we want to find the largest streak of blue, basically. But you can very clearly see, especially in the bottom one, I'm going to focus on that more. There's the weekly variation that I was talking about earlier. It's crystal clear, like to a T. So we applied the filters to all of these, and we got this, which is a lot better, right? You can see there's a very clear continuous acceleration in block C, even though there's that weekly variation we've now gotten rid of. The other ones do a little bit better. You can see block B in the beginning here is growing and growing and growing. It gets rid of some of the weekly variation. And block A is extremely spiky, so this filter doesn't do a whole lot for us. The thing is that there's one point, you might not be able to see it, there's one little red dot in the middle of this continuously increasing thing. And that sucks, right? Because we want to see the largest blue piece we can. This one guy is going to ruin it, right? This thing might be several weeks. This guy comes in, knocks it out, and now if we just blindly say who's going the longest, they're going to get sort of cut off. So this, by the way, so this is the output of the filter I was talking about, right? And this, just doing this 140 million times is pretty impressive to me, maybe to you. So we're going to do this. We're going to take the filtered values and we're going to make this new type of signal out of it. And it's going to be a binary signal. It's if that thing was blue, if they've got more followers today than they did yesterday, then this value is going to be 1. Otherwise, it's going to be 0. And we're going to take that binary signal, we're going to run it through yet another filter. And so what we'll get out of that is a value somewhere between 0 and 1. Right? If you've got 7 consecutive days where you do not have more followers than the previous day, that filtered result will be 0. If you have 7 good solid days in a row, then the filtered result will be 1. And so it should be somewhere in between most of the time though, because it's going to be alternating back and forth between 0 and 1. So this will take this binary signal, running a filter through it will convert it to another continuous signal somewhere between 0.75, 0 and 1. And we're going to take anything above 0.75. So this is sort of what it looks like. Looking at the bottom one again, the points on the top are where you got more followers today than yesterday. The ones on the bottom are where you didn't. And so that 1 point right there is the thing that would have screwed us up. But now we've gotten past it. This blog, once all filtered, they actually were accelerating their follower count for 48 days straight. That's unheard of, I think. So I sort of handpicked a few of these to look at up close. Like, I can't believe that. If anybody's gotten that many new Twitter followers every day for 48 days, let me know, because that's a month and a half. The other ones did pretty good, right? Before they were much fewer continuous days of growth. But even 36 days is crazy. 15 days is a lot of acceleration. So this is the sort of thing that we can apply this and go and now, like, if we really want to see if we missed anything, like maybe there was a really popular blog that like teenagers in Brazil knew about and we missed, we can find them this way. We can pick them up, we can remove all the noise and really know what is going on. And I think this is one great application. There's so many more. We can do this with page views, we can do this with whatever it is that we want. And to do it at scale is really, really exciting for us. So that's my talk. I hope you guys got something out of it. And I think we've got plenty of time for questions. Any questions? Oh, was that clear? Really? Yes.
When you're using Scalding and the matrix applications of it, does it? I mean, you're doing it grouping first so that you have a different to form the original matrix.
Yeah.
But once once that happens, it will automatically turn each column or each operation into a mapper, or does it actually do something more complicated?
So I've read through the code a little bit, and I believe what it's doing is it figures out which. Oh, sorry. The question was sort of more about the matrix multiplication in Scalding and what it's actually doing under the hood, really, in terms of mapping and reducing. So I believe what it does is it goes through and it uses those row column values, and it figures out which things need to be multiplied together, and then we'll group by those new IDs, and then multiply the things or add or whatever it is you're doing, the things in that group. And maybe it'll have two groups where you first group and multiply, then you group again and sum a vector. I'm not like absolutely positive about that, but I mean, if I was just trying to write that, that's where I would start. The other thing is to know how many reducers it uses, you have to give it some amount of information. It doesn't know how big this matrix is. So it will, there are different types of ways you can tell it to guess. You can tell it, give it basically a sparsity percentage, and say like 1% of this matrix has values, and it'll make a decision based on that. And the other thing is you can tell it how many rows and columns you expect it to have, and it'll make a guess based on that. And it works. That the matrix stuff is not super documented, especially, you know, tuning these types of things for like how many reducers you use and whatnot. So you're gonna have to dig through some code, but it's fairly clean. There's a lot of magic in the Scalding code. If anybody's written Scala and loves implicits and likes to just have things taken care of for them, there's a ton of that. They love that at Twitter, I guess. But once you kind of get a handle on that and you can see what's going on, it's fairly straightforward.
How long does it take to run that code?
I'm sorry?
How long does it take to run that analysis?
Minutes. Tens of minutes, probably, less than an hour. Yeah. But I think we could probably tune it up to, like I was saying, the more reducers you use, the better to a point. So we could probably tune it to run even faster, I think.
How many machines?
We've got about 100 machines with, I think, 16 cores each. Our cluster's relatively small in that way, but there's a lot of, I don't know, it's more storage-based than computation-based, I guess. It's several petabytes out of just 100 machines, which I hear is pretty heavy. It's written in, it's all written in Scala. So, I mean, they don't use any of the like Laiacano or any of the they don't use any of that. And the big thing is that if you think about you're running this on a distributed system, there's 100 machines, there's duplicated data there. You know, I guess Hadoop is designed so it could be in different data centers, but it shouldn't be. But I mean, the main performance hit is going to be in shuffling data around and aligning it. Performing the multiplications quickly is not at all your biggest concern. How do we come up with the definition of trending blog? I mean, most of our trending content is sort of like, you know, I'd love to get someone to give a talk about that. We don't use this for trending blog content. Most of our trending stuff is just sort of like, we look at the expected number of likes or reblogs or whatever, or in trending tags, the expected number of tags that would be used. And if it's like a huge outlier above that, then it's sort of like z-score related, I guess, right? You take the mean, divide by the difference from the mean, divide by the variance, and you get the z-score, and then just sort those. We use some version of that for the trending stuff that's really modified. I clearly don't know a whole lot about it, but that's on that line. But the trending stuff is all, our trending tags are actually calculated in real time. We consume our own fire hose and calculate it that way. Trending blogs like this would be done daily. So we don't actually use this for like trending content stuff because it's too slow. But is there a way to back up a Hadoop cluster? Yeah, if you have another one, there's a function called dist copy. If you have another Hadoop cluster, there's a function called dist copy that comes with Hadoop. Yeah, I stay away from the maintenance part of my Hadoop cluster as much as I can. All right, well, thank you guys.